So now we have to work with this model and see what happens. Now let us play with this small molecule. Suppose we will take up an actual organic molecule here, right? I will draw a molecule Cl, or we'll take a CHO, CH3, H and OH. We take this molecule. Now this is the same as, let's see here. Look very carefully. I told you the horizontal bonds are towards you. So I will write the horizontal bonds like this. That both of them are projecting towards you. Remember that. So I got H here, OH here, and I have two bonds behind which are vertically pointing up and down, CHO and CH3. Okay. Now, can we convert this in the wedge dotted line structure as we represent this? Can you convert this figure into this type of a structure? Okay. So you have to bring only one of them to the front, one to the back, and two groups should be brought. Two groups should be brought to the plane of the paper. Okay. Now this is a little bit, I will say, interesting exercise, but a high degree of imagination is required. Now what I will do is, I'll ask you to do is, along this axis, remember this is exactly pointing away from you, to the top side. It is not exactly away, it is something like it is away from you by an angle of 90 degree, 45 degree. Okay, now what you are doing is, you are rotating this whole molecule along this axis, along this carbon, through this carbon, you are rotating this clockwise. You are rotating it clockwise by just how much degree? Yeah, 90 degree. So the CHO group, which is projecting back side, will come to the plane of the paper. That is, the CHO will come here. It was like this, pointing backwards. Okay? It was like this, pointing backwards. Similarly, this CH3 also will come to this position. Okay? Now see here, this CH3, this OH. Remember, we are rotating by 90 degree only, not 180. So this OH, which is on the right hand side, will move through the front to the left hand side, like this. It's only 90 degree. It will move to the left hand side like this. And this H will move to the back side behind this OH. Are you getting this concept? I don't know. Let me remove this It's not required. I put the voice here. Okay, now I have to show you whether how this works. Let me bring the model and show it to you. Now see here, I will switch on my video. Okay, 2 more people are coming. Yeah. Now, see here, I have got the model. Let me assign the groups. Let me assign the groups here. CHO group, I will write it here. CHO. CHO is, which one will be CHO? One second. The red will be CHO. I keep the red as CHO. Orange. CHO is orange color. And the red one is CS3. Okay. Now see here. This is the model. You can do one thing. You can write down. This orange color is CHO. The green is OH group. The red is, which is the third group, CS. I think we have to struggle with the internet. I think we will have to struggle with the internet. Connection is highly unstable. I have taken 2 connections here. Still, let us see. Now see here. This is CHO. This is CS3. This is hydrogen. This is OH. Okay. Now see, both of them are pointing backwards. If you look from there, none of them are eclipsed. See the way I'm holding it. This hydrogen is towards you. This OH is towards you. The CHO is away from you, but pointing up. And this is pointing down. Where is the plane of the board? The plane of the board is in between here. And only the carbon is in the plane of the board now. 2 groups are away, 2 groups are towards you. Now what I ask you to do is rotate this 90-degree clockwise. See this? Just 90 degrees. Okay, let me share your board. Let me share the board. You can see what I have drawn there. Can you see it? See this? Oh, what I did is, yeah, CHO. I don't know how you are seeing it from there. Are you seeing this way? One second. Because I am seeing from the opposite side. You may be seeing like this or this. Let me write both of them. The right hand is, I won't be able to tell you. See, I don't know whether you see here. this CHO has come to the plane of the paper. This is the plane. I told you this is the plane of the board. See, if I rotate like this, I have the plane here, same. But now group is there. But I rotate 90 degree, the CHO will come to the front, to the plane, and CH3 also to the plane. Now see what happens. OH on this side has moved to this side. But still it is towards you. It has changed the side only. See here. It is towards you. And hydrogen, which was there in the front, has gone backside. Hydrogen is away from you, OH is towards you. That is what I have drawn here. I don't know whether you are seeing this figure or this figure. Is it clear? So this is, now I can just make this into this form. I have the OH here, H here. Okay. What should I do? I just have to rotate this over here, this over here, and this over here. So the CHO will come here. Okay. OH will come here, and not OH, CH3. CH3 will come here on the top, and H and OH will be here. So this is how you convert a Fischer projection into this. So this is the same as this. This is the same as this. Now I have told you, I have told you before, if you hold this, just hold it as such, you can interconvert these three. The molecule will not change. That means this is the same as, if you draw the structure like this, it is the same molecule. I can bring the CHO to the front. OH over to the back. And H onto this side. This rotation is allowed. Cyclic rotation is possible. Very similarly, you can do the same thing here also in the Fischer projection. That is, this is same as CHO. You can exchange them in this fashion only. Only in this fashion. So what do you get? H will come here, OH will come here, and CH3 will come here. Okay? You need not hold here. Suppose I can hold here also. Hold this. Don't change this. The other three can be changed. Molecule will not change. That's the meaning. This is the same as CH3. H is here itself. This CHO comes here. And the OH comes here. Okay. Now see here, compare this. Compare this and this. Both sides, H and OH, CHO and CH3 has got inverted. So in a Fischer projection, this inversion will not change the molecule. This inversion, what type of inversion? Side, both the side inversion will not change the molecule. It is just like I am looking from the front or I am looking from the back. I'm standing with my back to you or with my front to you. I remain the same. Okay. So this is what is a Fischer projection. You can play with Fischer projection. You can convert one Fischer projection into another one. Okay. So this is a second method of method of. Oh, somebody else is coming. Yes. One second. Let me see what I have recording. Yeah. So this is so we have studied 4 different methods of representing organic compounds. One is wedge dotted line structure, and the other is Schoffer's projection, which I have shown you here, Newman projection, and this one is Fischer projection. Now this is very commonly used in, it's very commonly used in carbohydrate chemistry. This Fischer projection is commonly used in carbohydrate chemistry. You are in second year, you must be knowing the structure of glucose. Or you are going to come across this structure so many times. H, OH, OH, H, H. Here is the structure of glucose. Okay, see this? This is a Fischer projection of glucose. What is the meaning of this? This is the meaning. The CHO is pointing away from you. And what about this H? The H is pointing towards you. OH is pointing towards you. Again here, this OH is backside. Again, this OH is on the right hand side. H, OH, and look, CH2OH is backside. This is the actual three-dimensional structure of this molecule as represented in this fashion. So whenever I draw like this, please, in your mind, you should have this picture. Now let us rotate this. Let us rotate this as we have done before. 90 degrees towards you. Your CHO will come here to the plane of the bond. And your OH will come here. And where is the H? H is on the back side, behind the OH. Now you do the same thing with all of them. Here the H is in the front. And here is OH. Next carbon, OH is in the front. Next carbon, again OH is in the front. That means H is in the back side. And you have the CH2OH here. Okay, this is very, very important as far as carbohydrates are concerned. You are going to face this problem. H here. You are going to fix this. Okay. Now you know glucose is having a cyclic structure. So what you have to do is close this ring. Okay. You will have a structure like this. If you close this ring, in which, see the way you have to write, in which, see here, this CH2OH is, actually this ring is not closed here, it is closed here with this OH. Okay? And that time, now, what we'll do is, we'll turn this around. I told you we can rotate these three, interchange these three, right? I told you this can be interchanged here. Sorry, not this one. I can use it this. See here. I can bring it here. I can bring the CH2OH here, H on this side, and OH on this side. So what I will do is, I will write CH2OH in the place of H. So see here, this CH2OH I'm going to place, or I will place CH2OH. In the place of H, yes. So I will make a change here itself. CH2OH in the place of H. So here I have to place a CH2OH. I will place a CH2OH here. And then I should place my H on the place of OH. So what I should do is simply remove this. And put the OH here. Yes. OH here. Okay. Now I close this ring. If I close this ring, look very carefully. You are going to face this, study this again in biochemistry. That's why I'm just giving you an introduction. Now see here, in this ring, in this whole ring, formed after removal of what molecule of water from this? Is it? No, it's not removal of water. It's just exchange of this one, a cyclic structure. Okay, see here. You will generate an OH here. One OH will be there. Now, this CH2OH, I will write on the top. Okay, so on the side of CH2OH, you have an H here on the next carbon. H. See dotted line. All dotted lines will come on the same side of the ring. All dotted lines will come on the same side of the ring. So next carbon, OH is here. Also, the CH2OH is down, up. This H is up. OH is down. Yes. H is up. On next carbon also, OH is down. Oh, here. 2OH. So this CH2OH, CHOH, CHOH, and here the H is up. Now where is that? One second. There is a small mistake. CH2OH is this is carbon number 1. Let me put this as 1, 2, 3, and 4. Now this is 1, 2, 3, and 4. Yeah. On the 1 you have the CH2OH. On 2 you have the hydrogen on the same side. On 3 you have the OH on the same side. Yes. On 3 you have the OH on the same side. H is on the opposite side. And what about 4? On 4 you have H on the same side. H on the same side. OH on the opposite side. Okay. And here this OH you can put either on this side or in the opposite side. So this is how you translate this bond, this Fischer projection, into a cyclic structure in carbohydrate chemistry. You are going to face this a lot of times. Okay. So you should be having some knowledge of how to convert this. So what you have to do is vertically rotate the molecule vertically clockwise. Okay. And imagine on which side all these groups. See, all these groups are on the same side. And these groups are on the opposite side. So that is how you have to translate this. Clear? So this is what is called Fischer projection. Now, let us see. Now let us see. I told you, let us come back to the optical activity. Let's tell you some technical terms. We'll take a simple molecule. 2-butanol. We take 2-butanol. Structure of 2-butanol is CH3, CH2, CH, OH, and CH2. This is the molecule. You have a chiral carbon. This carbon is chiral. So I will write this. I will write this molecule in this way. Your textbook is given very funny figures, which I don't like. No other textbook will give you. CS3 I'll put here. I got the OH on this side. This is H, and I got C2H5 here. So here is a mirror image of this molecule. There is a mirror image. Remember, the mirror image on the right hand side group will be coming on the left hand side. No other change. They are not superimposable as we have seen yesterday. And these two are entirely two different compounds, and you call them as enantiomers. You call them as enantiomers. Okay. If I have to say if, I told you if this is dextrorotatory, this will be levorotatory. If this is plus, if it is dextro means plus, this will be minus. Minus rotation means rotation of plane polarized light using negative side. Anti-clockwise. And plus means rotation of this in the clockwise direction. Okay. So this is so here you have only one asymmetric carbon. One asymmetric carbon. And if you take an equal mixture of this, equal mixture, which you call as DL mixture or plus minus, this is called racemic mixture. Racemic mixture. Okay, and its optical activity is 0. Optical rotation. And you must be knowing, equal amount of two substances will rotate one to the right and the other to the left. And so the net rotation will be 0. Okay, so that is what is called a racemic mixture. Now, suppose you have two chiral carbons. So if you have one chiral carbon, there are two forms. Okay, so the number of chiral carbon is related with the number of structures with this formula, 2 power n. So if you have one carbon, you have 2 power 1 equal to 2 forms. There will be two forms, and those two forms I have drawn here. Suppose I have two carbons which are chiral. I will have 4 forms. Let us see. Well, let us take an example. We will take an example which is here in your textbook. 3-chloro-2-butanol. Three-chloro-2-butanol. Structure butanol 1. Oh, did I increase it? Oh, 1 is extra. 1, 2, 3, 4. Now 2-chloro. So I'll put a chlorine here and an H here, OH here. So it is 3-chloro-2-butanol. Is it 2,3-chloro? Yeah. Yeah, it is right. Numbering has to go from here. 1, 2, 3, and 4. So I should get the least number. So 3-chloro-2-butanol. Now, I can draw this in 4 different ways. First of all, let me draw. I will draw only Fischer projection. Okay. So I will put this is CS3, sorry, CS3, and this is also CS3. So here is my first carbon, the carbon 1, and this is CH3. Here I have OH group. I got the Cl here. H here and CH3 here. So this is one way of writing it. Now I will draw the mirror image of this. Here is a mirror image. CH3 will remain as 6. OH is here. Look very carefully. Cl here. H here. And CH3. You have drawn just a mirror image. What is the other? So two possibilities we have done. What is the third possibility? The third, here what we have done is we have inverted in each point. The third possibility is I'll invert, I'll keep this as such. And invert only the one which is below.